hope you had a good weekend. This is the lecture for Tuesday, May 5th. You should have already have gotten an email from me probably Sunday night detailing and talking about that test again, which is coming up on Thursday. That's my only announcement. So you have a test in 2 days. That test is on chapters 6 and 7. I'll talk about that test a little bit later. We're going to work on chapter 8 in this video. So you should have gotten that email detailing again how this test is going to work, where you're going to call in on your cell phone by way of Zoom, and you'll take the test while I watch you through your phone. But you got that email and you've read it carefully. I will be strictly sticking to those guidelines, so there won't be excuses. But again, we'll talk about that later. So that test is on Thursday the 7th, so 2 days from now. We finished chapter 6 and chapter 7 last week, and we're ready to move on to chapter 8. So basically what's left is 3 sections in chapter 8 where we kind of pick through them and pick certain ideas and talk about them, and then 4 sections in chapter 9 where again I kind of pick through them and talk about certain ideas in each one of those sections. Both of those chapters, the 3 sections in 8 and the 4 sections in 9, will be reflected on a quiz number 5, which will come out after this test. So it'll probably come with the handouts in next Tuesday's lecture. And then there's just the final after that. And you should have gotten that schedule as well that I emailed to you in terms of what's left. I'll also be emailing you a review packet. It'll probably come after you take that test, just to give you a day to calm down. And that'll come by way of Canvas email as well. So let's start with chapter 8 and see what we can do with it. So let me go grab my first section, which is 8.1. So we do 8.1, 8, oh boy, I forget. 8.1, 8.5, and 8.6 in chapter 8. And section 8.1 is about systems of linear equations, but it's more than what you've learned in the past. So in college algebra, we really do assume, we don't review this, the notion that you have in both beginning algebra and intermediate algebra discuss the idea of solving systems of linear equations, where you have 2 equations and 2 unknowns. And I assumed that you know how to do that even in an earlier chapter when we talked about using substitution to solve and get rid of one of the variables and only have an equation with 1 variable in it instead of 2 equations and 2 variables. What we're going to kind of hit on in section 8.1 is solving a system of equations that have 3 variables and 3 equations, and how we deal with that, even though it's linear. And it will depend upon, it will be based on the idea that you already know how to solve a system of 2 equations and 2 unknowns, which is either using elimination, where you get the same but opposite coefficients on either the x's or the y's, or by using substitution. If it looks easier, you solve one for a variable and substitute it into the other one. We kind of looked at that, like I said, a couple of chapters ago. Mostly we'll probably do the idea of elimination with this particular type of system of linear equations. But I want to discuss just a little bit what it means to have 3 equations with 3 variables. So I wrote down systems of 3 equations with 3 variables. And it says that the graph of an equation with 3 variables is a plane. So we're now in 3 dimensions. And this is actually a topic you'll get to in calculus, but not for a while. I think it's in Calc 3, where you talk about this idea of 3 variables and 3 equations, and what does that look like. So basically, if you have an equation that has 3 linear variables in it, you're talking about a plane, so 3 dimensions. So the idea of this wall being a plane, or just this, because a plane again is infinite in all directions. So this wall right here in my garage is a plane, not just the whiteboard, but if I extended the whiteboard and it just kept going in all directions, that's a plane. And that's something that we're talking about when we're talking about 3 variables being in a plane. It is 3-dimensional. so it's hard to deal with when we're looking at a two-dimensional surface. But now what we're interested in doing with 3 equations and 3 unknowns, or 3 variables, is seeing if we're doing a system, we're trying to see where they intersect. Just like when you did a system of 2 equations and 2 unknowns, you were trying to see where those 2 lines, because they're linear, where they intersect. And if you recall, 2 lines can intersect in a point, right there where my knuckles hit, or 2 lines can be parallel and never intersect at all, or 2 lines can actually be disguised and be the same line, and they intersect everywhere. So you can either have one, we would have an ordered pair as a solution, or we would have no solution because they never intersect, or we had infinite amount of solutions, the line itself, if it was the same line, just disguised nicely. Well, the same sort of idea happens with planes in 3 dimension, except, so I'm going to get a visual here, or at least try to, except that 3 planes, since we've got 3 variables, 3 planes can intersect in one of 3 ways. So one way is, so here's my one plane, the wall. Normally in the classroom I would have you look at a corner, but I can't really do that in the garage because the ceiling of our garage isn't horizontal. So I'm going to try and use these as my ceiling and another wall in the garage. So the idea here is if this is a plane, and then I take another plane and I shove it through this wall in my garage. So again, you have to imagine that these are infinite. And then I take a third plane and I shove it through this wall in my garage. The question is where are those 3 planes intersecting? So certainly this plane intersecting with this plane, the wall, intersects in a line right here. It's an infinite amount of solutions. It's not just a segment. Remember, again, this keeps going forever. And if I throw the ceiling in, this ceiling intersects in this line with this wall. But now I want to know where all 3 of these are intersecting. And these 2 are intersecting in this line up here in the corner. But the question is where all 3 of them, what do all 3 of them have in common? And if you really think about it and you look up in the corner of your room, what do they all have in common is actually just the ordered triple, which is, let's see if I can hold these all at the same time, probably not. The ordered triple, which is right there, the corner of the intersection of those 3 planes. So if you look in the corner of your room, there's an ordered triple right there, believe it or not, x comma y comma z, which represents where those 3 planes intersect. So 3 planes can intersect in what's called an ordered triple. And in fact, so I'll tell you a little story here that Descartes, who actually came up with the Cartesian coordinate system, the XY axis that you're used to. There's also an XYZ axis, that's 3 dimensions. Descartes came up with that as well. And the story goes that apparently you have to be delirious with fever to come up with anything brilliant. So apparently Descartes was in his room, in his bed, delirious with fever, and he spotted a spider, or some sort of a bug, in the corner of his room, and he started watching it as it swung on a web, or swung on its little string of web, and went to another area, like on the ceiling, then it swung down and went onto one of the walls, and he started to try and track it, or then it walked on the one across the wall and then swung again on its web. He wanted to try and track it, and he wanted some way of being able to figure out where that spider was in space. And that actually is presumably what started the idea of 3-dimensional X, Y, Z axis, and how can you actually pinpoint where that spider would be. So you can keep that in mind when you get to Calc 3, when you start talking about X, Y, Z axis. But mostly what we're interested in is where can they intersect. So 3 planes can intersect in an ordered triple, just like 2 lines can intersect in an ordered pair. But there's also the option that 3 planes don't intersect at all. So in other words, here's the one plane, my garage wall. here comes the other plane right here, parallel to the wall of my garage, and here comes the third plane right here, parallel to the wall and this plane as well. So we have 3 planes here never intersecting. So that means the intersection or the solution to the system would be the empty set. One more option of 3 planes is that 3 planes can intersect in an infinite amount of solutions, basically a line. So in other words, if I remember when I took this guy and put him up here, and I said these 2 planes intersect in this line, and then I put this one up here, but I'm not going to do that this time. I'm going to take this plane and I'm going to come at an angle, maybe a 45-degree angle or something, and I'm going to cut right through like that. So where are all 3 of these planes intersecting? All in this line right here, which is an infinite amount of solutions. And specifically it would be a line, and we're not going to work real hard to figure out what that line is, but we're just going to recognize when it is that we have an infinite amount of solutions and when it is that we have no solution at all. So we have 1 of 3 options, just like with 2 dimensions. Either they intersect in an ordered triple, or there's no solution because they don't intersect, or there's an infinite amount of solutions because they actually intersect in a line. So let's go take a look at what I've got here in terms of the directions for figuring this out. So I wrote down, solving a system of 3 equations with 3 variables uses a series of eliminations. So the first thing we're going to do is we're going to take 2 of the equations and pick on one of the variables to try to eliminate using the elimination process. And then we'll take 2 other equations of those 3 that we have and eliminate the same variable. In other words, our goal here is to try to reduce the 3 equations and 3 unknowns to 2 equations and 2 unknowns. Step 2 is once you have 2 equations and 2 variables, we'll use elimination or substitution, which again we're assuming you all know how to do, to figure out those 2 values. Once we have those 2 leftover values, we can plug it back into the originals and figure out the 3rd unknown, if there is one, if it isn't a special case. So we're only going to do 2 examples of these because again, this is just us, we're just trying to introduce you to this idea of, hey, there's more than just 2 unknowns and 2 variables. So this very first one, again, to show that it's a system that they want you to solve, so this is 8.1, they put a little brace around it, and the directions are just solve. So let me get this written down. So they want me to solve the system of equations, and I notice that there are 3 equations and 3 unknowns, an x, y, and a z. The minute you have 3 unknowns, then you need to have 3 equations in order to figure out how to solve it. This means solve them simultaneously. In other words, where do they intersect? So either an ordered triple, they don't intersect at all, or they intersect in an infinite amount of points, which would ultimately be a line. So how do I figure this out? The goal is to turn this 3 equations and 3 unknowns into 2 equations and 2 unknowns. And so you need to be really systematic about this. I actually have some kind of organization. I actually number them because it helps me with the organization so I can see what I'm doing to them. And what I'm going to do is think about the elimination process, which is, can I create opposite coefficients for either the x's or for the y's or for the z's, which looks easier? So by that I mean, certainly equation 1 and 2, I could eliminate the x's by taking equation 1 times a negative 2. Then I have to pick 2 others, so I could guess I'd go with, I wouldn't want to do 2 and 3 because that would be harder. I'd have to turn both of those into opposites. I could go 1 and 3 and turn x into negative 5x by multiplying everything in equation 1 by negative 5. So that's one way to do it, but I'm going to keep looking because that doesn't look as easy as I would like it to look. So I'm going to look at the y's now and see if they're easier. And notice that this is nicely set up for me. All the same variables are underneath all the same variables, equals are under equals, and numbers are all over here on the right-hand side. You do want to do that. It makes life easier. So now I'm going to compare the y's. Right away, here's what I noticed. Look at this. 1 and 3 are ready to go. I don't even have to adjust them. I can use elimination and the y's will go away. And then I can either do pair 1 and 2. That would be a little harder. Then look, 2 and 3, all I have to do is multiply 3 by 3. And the y's, I can eliminate the y's. So right now I think y's look really easy. I take a quick peek at z. Yeah, the z's aren't too bad, but the y's win for me in terms of being the easiest. Does it matter? Can you pick a harder? Yeah, I mean, I could have eliminated the x's or the z's, but the y's look easier, so I'm going to do them. So here's the deal. I'm going to tell myself, so in other words, keeping myself organized, I'm going to use equation 1 and equation 3 and eliminate the y's. So I'm choosing to eliminate y's. So here I go. 1 and 3, they're ready to go. I don't have to do anything to them. And I've got 5x plus y minus 2z equals 12. This is ready to go, ready for elimination. I'm going to add these two together. So again, I'm assuming that you know how to do elimination. I'm going to add these two together and the y's will go away. So this gives me 6x, and again, important, you have to have like terms lined up, everything lined up underneath each other, or else this process doesn't work. Y's are gone. This gives me a negative z equals a negative 4 plus 12 gives me a positive 8. So this first equation now that I've generated by this elimination process is an equation that has no y's in it. So I'm going to call this A because I already have 1, 2, and 3, and it gets confusing if I use 1 and 2 again. So here's my first equation where I'm down to two unknowns. I'm going to do it one more time with something other than 1 and 3. So in other words, either pair 1 and 2 or 2 and 3, which is the easiest that we thought about for the y's. I think it would be easier to do 2 and 3 because then I don't have to fool with signs. So I'm going to take equation 2 and I'm going to leave it alone. 2x minus 3y plus 4z equals negative 15. And equation 3, what do I have to do to equation 3 so that there's an opposite coefficient here? I have to take this times 3, right? Which means the entire equation 3 times 3. So I actually write myself a note as to what I'm doing to it. So here I didn't do anything because they were ready to go. This one I'm going to take 3 times equation 3. So I have a 15x plus a 3y minus a 6z equals 36. So everything times 3, both sides. 15x, 3y, negative 6z, 36. Now these are ready to eliminate, and I should just get an equation that has x's and z's in it if I'm doing what I think I'm doing. This gives me 17x. The y's are gone. The z's give me a negative 2z equals, and 36 and a negative 15 is going to leave me with a positive 21. An equation with just an x and z in it. An equation with just an x and z in it. I'm going to call this equation B. So now what have I done? I've taken a system of 3 equations and 3 unknowns and turned it into a system of 2 equations and 2 unknowns, the same unknowns. This does not do you any good if you eliminate y's here and you decide to eliminate x's here. You're not getting anywhere. I have to eliminate the same variable in both sets so that I now have an equation that just, 2 equations that just have x's and z's in them because I chose to eliminate the y's. So now I'm going to do elimination again. So the question here is, so this is equation A, this is equation B. Who do I want to eliminate, x's or z's? Well, I think z's looks a whole lot easier than x's do because I'd have to turn both of these into a number that they both go into. So I'm going to choose to take equation A. This is a negative 2z, so this needs to be a positive 2z. So I'm going to take it times a negative 2. So I'm going to take equation A times negative 2, and I'm going to leave equation B alone. So when I take negative 2 times equation A, I get negative 12x, positive 2z equals negative 16. Everything times negative 2. Negative 2 times negative 2 times negative 2. Equation B, I'm thinking leaving it alone will work. 17x minus 2z equals 21. This is ready to go now to eliminate the z's. So this gives me 9x, z's are gone, equals 21 minus 16 is, so what did I do wrong? Oh, I know you're all screaming at me, right? It's hot here in the garage. It's been a long day. 17 minus 12x doesn't give you 9x, does it now? It gives me 5x. 5x equals 5. Why did I think I did something wrong? I mean, oftentimes, yes, you do get nasty numbers and fractions, but I happen to know that this one wasn't going to give me a fraction because I'm trying not to give you something like that as your one example for how to do these. So I get 5x equals 5. I divide both sides by 5, so x is equal to 1. The fact that the x's, that I have a variable and I get an answer means that this is going to be an ordered triple. In other words, I got a value for x, so that means y has a value and z has a value, and this is one of the ones where the three planes intersect in that corner in an ordered triple. So x is equal to 1. So now how do I get the other values? Well, I backtrack now. So don't plug x equal to 1 into one of the originals. There's too many unknowns there. Plug x equal to 1 into one of these two, into the A or the B, whichever one looks easier, to get the second value, which will be z. So which one would you like me to plug this in to? I think A looks a little easier, so I'll go, because the numbers are smaller, so I'll go put it into A. So when I plug this into A, I get 6 times x, which is 1, minus z equals 8. So that gives me 6 minus z equals 8. I subtract 6. I get negative z equals 2. I divide by negative 1, and I get z equals negative 2. So there's my next value. So that came from A and B, x and z. Now what do I do to get the last missing values? I plug x equals 1, z equals negative 2 into any one of these three, because it has to work in all of them. So which one would you like me to plug this guy and this guy into? Which one looks the easiest? Maybe number 1, because again the numbers are all a little bit smaller. So I'll plug these into number 1. I've got x, which is 1, minus y, which I don't know, plus z, and z is negative 2, so minus 2 equals negative 4, and I'll solve for y. So that gives me negative 1 minus y equals negative 4. I add 1, I get negative y equals negative 3, so y is equal to positive 3. So my final answer here is that this is an ordered triple, and the way you write it is x, y, z. So 1, comma, 3, comma, negative 2 is the ordered triple that these three planes intersect in. And in fact, I know these work in number 1 because that's where I've put them ultimately into, but they should also satisfy number 2 and satisfy number 3. So you can always double check. When x is 1, y better be 3, and z better be negative 2. Well, that gives me 2 minus 9, so that's negative 7, and negative 7 minus 8 is negative 15, so that looks good. And they should work here as well. 1, 3, negative 2. This gives me 5 plus 3, which is 8, plus 4, which is 12. So now I know I've got it. And I feel good about what went on. So if you get a solution for x, then that means that you have to go and get your y and your z or whoever you got the solution for, and it's going to be an ordered triple. So what do those special cases look like? So let's go take a look at number 2. Let's see if I can manage not to think that 17 minus 12 is 9. second one, again, I see the brace, so this is telling me they want me to solve a system. It's all written down very nicely. Dog. So they want me to solve this system, and I notice it's 3 equations, 3 unknowns. So I'm gonna number the equations just to help me with my organization of what I'm gonna do. I'm gonna try and do a series of eliminations. So first of all, I have to decide who looks easiest to eliminate, x's, y's, or z's. A couple of times, because I have to do this twice to get it down to 2 equations and 2 unknowns. So the x's, that negative x with that, the x's wouldn't be too bad. I would have to take this times 2 to get it to go away with number 1. I would have to take it times 3 to get it to go away with this one. So not bad. The y's don't look that nice at all, because the second one and the third one look okay, but then I have to play a little bit too much to get the second set to go away. But look at the z's. Oh my gosh. I'm going to go with the z's on this one. Could I do the x's? Absolutely. But the z's look even easier. So I do take a few seconds just to think about who I would like to do. So I'm going to propose that we eliminate the z's. So that means that, well, 1 and 2 are ready to go. Look at that. Negative z, positive z. I don't even have to do anything to them. So I've got 2x minus 3y minus z equals 0. And 2 is negative x plus 2y plus z equals 5. Ready to go. So I add those two. I've got x, negative y, z's are gone, equals 5. So positive x minus y equals 5. There's the first set. Now, something other than 1 and 2. So when I'm noticing what's ready to go is 2 and 3 as well. So I'm going to do 2 and 3 now. So 2 and 3. So don't do the same 2 again. You won't get anywhere. You'll just be spinning in circles. I've got negative x plus 2y plus z equals 5, and 3 is 3x minus 4y minus z equals 1. Again, I didn't have to do anything to those to get the z's to eliminate. So this gives me 2x, this gives me negative 2y, z's are gone, equals, and this gives me 6. So now I have 2 equations, the same 2 unknowns. So I'm going to call this equation A and this equation B, and I'm going to think about trying to now do elimination on it so I can get down to 1 unknown and 1 equation. So what looks easiest to eliminate? Well, the x's don't look too bad. I'd have to take this times a negative 2. And the y's also don't look too bad, do they? I'll just go ahead and eliminate the x's just because they both look equally easy to get rid of. So if I decide to eliminate the x's, I'm going to have to take equation A and multiply it with negative 2. So I'm going to tell myself that's what I'm doing. I take negative 2 times x, I get negative 2x. Negative 2 times negative y is a positive 2y. And negative 2 times 5 is negative 10. So everything times negative 2. Be very careful with those steps when you're doing them. Make sure you do it all the way across. Not just on one side of the equation, on both sides. And equation B, I believe I can leave alone and the x's will eliminate. And then minus 2y equals 6. But look at what happens. Not only am I eliminating the x's, but look at what else is happening here. The y's are also going away. The minute your variable gets eliminated completely, all the variables get eliminated completely in this process, it means you have one of 2 special cases. Either the planes are parallel and there is no solution, or the planes intersect in a line and there's an infinite amount of solutions, or it's the same plane and there's an infinite amount of solutions. So everything over here goes away and I have 0 over on the left side, and on the right side I add these 2 and I get negative 4. So here's the deal. The variables are gone. So special case, I just have to decide which one is it. Is it no solution? Or is it an infinite amount of solutions? Well, if the variables are gone and it is a false statement with the numbers, then that means there is, same thing we've done before with different applications, that means no solution. So this is the one that is, there is no solution. So either the empty set symbol or you write down the words no solution. Do not leave me hanging. Don't go variables gone, false statement, and then go to the next problem. You're not done yet. You haven't told me what the solution is. There's either an ordered triple, or there's no solution, or there's an infinite amount of solutions, which would be the line where they intersect, and we're not going to try and find it. In fact, this is my last example on this. So how do I know it's the other case? So if I did all this and I got 0 equals, because this side will be 0 if all the variables going away, and lo and behold, everything over here ended up going away as well. So in other words, I ended up with 0 over 0 when I did this. Here the variables are gone as well. But this is a very true statement. And if you have a true statement, in the past that meant all real numbers, right? But that isn't how we describe planes intersecting or lines intersecting. It's not all real numbers. It's either it's the same line, or if it's planes intersecting, then they're intersecting in a line. And right now we're just going to say that there are an infinite amount of solutions. In general, it's either the plane itself or it's the line where the plane, all three planes intersect. So we're just going to leave it here because the rest of that is a little more complicated to figure out. Okay. And that's all we do in 8.1. So just kind of reviewing the idea of systems of equations, then making them a little more complicated, making it 3 equations and 3 unknowns and how to deal with that. So we're ready to move on to 8.5. So I'm going to get rid of this stuff. So yeah, I'm doing this on one of those really hot days that we had, I don't know, it's probably a week and a half ago or something compared to when you're watching this. And you can, I don't know if you can hear it or not, but you can, a lot of the foghorns are going off on the beach because of all the oil tankers and things that are out there. So it can, I can hear them, I don't know if you can or not. Alright, so 8.5. So 8.5 is a section that actually will be very useful to have knowledge of when you get to, I believe that this gets done in Calculus 2, in Calc 2. It's called partial fraction decomposition. Wow, complicated sounding name, and it's actually a process you'll need to know how to do in order to integrate difficult integrals. And I know those are words that maybe you've never heard, but they have to do with calculus concepts of trying to, so we talked about deriving or a derivative with the other shirt I wore a while ago, and now this is integration is actually the reverse of differentiation, and it's a process you'll learn in calculus. And sometimes when the integrals are difficult, it's because the integrand needs to be manipulated algebraically, and that's actually why I keep commenting that sometimes students don't get through calculus, but it's not so much that they don't understand what they need to do in terms of the calculus steps, but they can't get it accomplished because their algebra gets in the way. So this is an algebraic manipulation that you need to know how to do in order to do the calculus steps. So this thing called partial fraction decomposition, if you read what it says that it's the process of writing a rational expression, so an algebraic fraction, into the sum of the simpler fractions that it actually came from. For example, I said if you wanted to try and take 5x minus 1 over x squared plus x minus 12 and change it back into the simpler fractions that it came from that had been added together, this is the process that helps you to be able to do that. So let me just take a peek at that for a moment. So I have 3 over x plus 4 plus 2 over x minus 3. That's what the fraction started as But then when you combine them, you get an answer that's now in an integral, and you can't figure out how to integrate it. The idea is you want to bring it back into this form, and that's what this process is going to be about. But just to remind you, here's what's going on here. So in the past, if I asked you to add these, what would you have to do? You'd have to get a common denominator, right? So you'd look at the factors to see and compare. Can I factor x plus 4? You tell me no. Can I factor x minus 3? You tell me no. They're both linear already, nothing to do to factor them. And they have nothing in common. No factors in common other than 1, which doesn't do me anything, which means the LCD that I would have to get would be one of each. So in other words, I need an LCD of x plus 4 and that x minus 3. So this is way back, I think maybe the review chapter, I don't know, a long time ago. So how do I turn these into this? Well, I came up with my common denominator, and then I looked to see what I have to do to change the numerator, and you tell me, well, what happened here is I put an extra factor of x minus 3, so that means I took this times x minus 3, so that means I need to do the same thing to the top, and I encouraged you to multiply it out. So this you distributed, and you got 3x minus 9. This guy, to get from here to here, you have to multiply by x plus 4. Whatever you do to the bottom, you do the same thing to the top. And then I said, what's the new numerator? So I encouraged you to multiply. There's my plus sign, so I don't have to worry about it. This is a positive 2. I distribute a positive 2. I get 2x plus 8 here. And then we took this, and we were ready to combine them. So keep the denominator, which is x plus 4, x minus 3, and add across the numerator. So 3x minus 9 plus 2x plus 8. I combine my terms, I get 5x minus 1 over x plus 4, x minus 3. And I used to let you leave it that way because actually then we tried to simplify this. So I looked to see if I can factor this, and I can't. And so this shows that nothing canceled. Typically in an integrand, they're not going to be so nice in calculus, and they'll actually have this multiplied out. So they'll have 5x minus 1 over, that's x squared, minus 3x plus 4x, so plus x, minus 12, and that's the guy that I gave you. Take a look. 5x minus 1 over x squared plus x minus 12. That's what's in the integral of this calculus problem. And there's no good integration formula that I can see that works on this. So what I need to do now is to take this and turn it back into this. Oh boy. Without having to necessarily figure all of this out. There's actually a nice way to do it if I can use the 4 formulas that I have written down below. So the goal here is to take this and turn it back into those 2 separate little more simple fractions that actually have a nice way to integrate them in terms of the integration formulas. So that's what this section is all about, is doing the algebra part of all of that. So you'll notice underneath, so it says after being rewritten as described below, the equation will be solved using methods for systems. Oh boy. So I have 4 things written down, and these are actually formulas for how to deal with the different kinds of more complicated algebraic fractions, how to turn them into the simpler fractions that they came from by following the formulas I've written down, which means I have to be able to identify them. So notice there are 4 of them. The first one says, if you have non-repeated linear factors in the denominator. So in other words, all of the factors are linear and none of them are there with a multiplicity. So none of them are squared or are cubed, or they are more than once. So that x plus 4 and that x minus 3 is only there once. They're both linear. The power on each one is a 1. If that's the case, then we take this guy and we rewrite it as an a over the x plus 4 and a b over the x minus 3, and then we look at the algebra to solve it, and that's what we'll be doing in a minute. But what if it's not 2 linear factors or just linear factors down here in the denominator? What if it's linear factors in the denominator, but Some of them are repeated. So look at the second example. It says, what if that denominator is x plus 4 and then an x minus 3 squared? They're both linear factors, but that x minus 3 is actually there twice, x minus 3 and then another x minus 3. That gets rewritten as a over the x plus the 4, b over one of those x minus 3's, and then you put a c over both of the x minus 3's, so x minus 3 squared, and then you solve that algebraically. Wow. Third one says, what if they're non-repeated, if there's a non-repeated quadratic factor in the denominator? So notice, take a look at that denominator. I've got x plus 4, and then I've got an x squared minus 3. The x squared minus 3 can't be factored further with our normal factoring methods. So I have a linear factor and I have a quadratic factor that can't be factored more. So that gets rewritten, and it's not repeated, it's just there once. That gets rewritten as a over the x plus 4, and look at that, bx plus c over that x squared minus 3. So we introduce an extra x on the top, and that gets solved algebraically. The last one, what if it's a quadratic factor in the denominator and it's repeated? So there's that x squared minus 3, but I put it there twice, so I have a power of 2. That gets rewritten as ax plus b over x squared minus 3 plus cx plus d over that x squared minus 3 all squared. Wow. And then that gets solved. So I've got the formulas here, but I still haven't looked at how things get solved, and I did comment up above, after being rewritten as one of these formulas, then I will solve the equation by using methods for systems. So that idea of systems of equations is coming into play again in this section. So let's go take a look at a few of these, because it'll probably be the easiest way for me to show you what's going on. Honestly, in a calculus book, they're probably not going to have this factored out for you. They would probably have this written as x squared plus x minus 2, but I'm trying to be a little bit nice here, and I have this one factored already for you. So here's the algebraic fraction, and they want me to find the partial fraction decomposition, which means they want me to figure out what this came from. What little smaller fractions did this come from? In other words, can I somehow split it up? So what I first have to decide is, which of those formulas does this follow? So what I see here is a linear factor and another linear factor, all linear factors, none of them repeated. So which formula are we talking about? We're talking about that very first one that says non-repeated linear factors in the denominator can be rewritten as, so I'm going to write down equals, a over the first linear factor plus b over the second linear factor. So this is the formula I'm using in order to split this apart. That's just the very first step. We've got lots more to do here. So we're saying this can be rewritten like this, but that means I need to figure out what A is and what B is so that I know how it can be rewritten. How the heck do I figure out the A and the B? And I know you're looking and go, but we don't know the X either. We don't need to figure out the X. Remember, we're just trying to take this fraction and rewrite it as two partial fractions. They're going to have X's in them. I just have to figure out what these guys need to be, what these constants or numbers need to be in order to make it a true statement that this is equal to this. So how do I figure this out? Well, this is now written as an equation. And what kind of an equation is this? It's a fractional equation, right? Or an algebraic rational equation, or algebraic fraction equation, which means what's the easiest way to solve an equation that has fractions in it? Multiply every term or both sides by the LCD. Well, what is the LCD in this problem? Well, it sure looks like to me that the LCD is x plus 2, x minus 1. So I'm going to take every term, there's 1, 2, 3 terms total, times x plus 2, x minus 1. X plus 2, x minus 1, x plus 2, x minus 1. So I'm going to go do this and see what I end up with. So when I multiply this side, the entire denominator cancels, which is the goal again, to get the denominator to go away, and I get 3x. When I take it times the second side, so this first term, the x plus 2 cancels, which was the goal here. But now what do I have to multiply here is I have to take the a times the x minus 1 to do the multiplication. So I get ax minus a when I take a times x minus 1. The second term, the x minus y's, x minus 1's cancel. And I'm left with a positive b multiplying with x plus 2, do the multiplication. So plus bx plus 2b. There's actually a couple of ways to do the algebra part of this. I'm teaching you this way in college algebra. Once you get to calculus, they might show you a slightly different way. Both ways work. We're doing it this way because we've been talking about systems of linear equations anyway, so we're going to go ahead and do it this way. So I multiplied everything out, and here's what I've got. And you go, oh my gosh, how do I solve that? There's too many unknowns. This is one equation, and I've got a's and b's and x's, but x's really aren't part of what I'm trying to figure out. I'm really just trying to solve for a and b. Here's the deal. So here's kind of a new technique to solving something like this. The fact is if I told you that if I told you 3x is equal to some amount of x plus some constant, I think you would tell me, so this is some amount, I don't know how much, I think you would tell me that the constant would have to be 0, right? Because I'm not adding anything to that 3x, and in fact, that guy right there would have to be a 3. And that's what we're going to do here, is we're going to pull this apart, and I'm going to pull apart, I have two unknowns here, basically, the a and the b. I'm going to pull apart into a system of equations. I'm going to strip off coefficients, and first thing I'm going to do is I'm going to look at my highest power of x over here, which is just x, and I'm going to go collect the x terms that are over here, which are these two. And basically, if I could add ax plus bx, I would have to get how much x? I'd have to get 3, right? Which means the a and the b, when you add them, need to give you 3. So I'm going to pull off coefficients and say a plus b has to equal 3. A plus b has to be 3. So I'm pulling off the coefficients and equating them. And then I also have, so I had x's, but I also have constants here. So my constants, I have a negative a plus 2b. There's no x's in either one of those. What's my constant over here? It's 0, right? So that means negative a plus 2b is going to have to equal 0. Just like over here, this constant was going to have to equal 0. And this was going to have to equal 3. Same idea, you strip off the coefficients. So a plus b has to give me 3, and negative a plus 2b is going to have to give me 0. So what I have here is I have a system of equations. 2 equations, 2 unknowns. I could figure this out. And in fact, elimination, this is ready to go. So I don't have to do anything. I'm ready to do elimination on this. When I add, the a's go away. This gives me 3b equals 3, which says b, when I divide both sides by 3, I get b is equal to 1. So there's one of my answers. And if b is 1, how do I figure out what a is? Plug it into either 1 or 2. It looks easier to plug into 1, but I'll check it in 2 as well. When b is 1, I've got a plus 1 equals 3. So a is equal to 3 minus 1, which is 2. And I'll make sure we're saying b is 1 and a is 2, so that's negative 2 plus 2, that gives me 0. So just as a good check. So that means that. So here's my final answer. That means that 3x over x plus 2, x minus 1 is equal to a, which is, that's equal, a, which is 2 over x plus 2, plus b, which is 1 over x minus 1. So all of that work just to take this fraction and turn it into its pieces broken apart So that then in calculus, I can take what's called the integral of each one of these and get an answer. And of course, you could always check this by trying to combine those, getting a common denominator and making sure that it all works. So partial fraction decomposition. All right, so we're ready for the next one. Let's go see what we can do with it. So kind of fun, maybe, figuring out the pieces of the puzzle. And a different way of coming up with the equation to get that solved because there were too many unknowns. And that often is a process that is very useful when you have too many unknowns and only one equation. Sometimes you're able to pull it apart like that and come up with a whole new system where I have enough equations for the amount of unknowns that I have. So number 2, they want me to do partial fraction decomposition on it, and it says, let's get -1. So 2x plus 4 over x cubed minus 1. So I look at this one and oh gosh, they didn't talk about anything where it had a cubed in it. We had linear pieces, factors, we had quadratic factors, but I didn't see any formula there for a cubic factor, which means I probably can factor this. So let me think about this. This is the difference of cubes, and when I factor the difference of cubes, how do I do that again? So x cubed minus 1 factors into a binomial and a trinomial. So x cubed minus 1 again. And how do I get those? The binomial comes from the cube roots. Cube root of x cubed is x. Cube root of -1 is -1, or keep the sign. How do I get the trinomial? I use these guys to generate. I take this guy times itself, or square it. I get x squared. Middle term is multiply these two and change the sign. So that gives me -x, so I'm going to write down plus x. And then square this guy, or -1 times -1 gives me +1. This should be prime if you've done things right. When you try to factor that, you're not going to get anywhere. Something that is the easy big X, something that multiplies to 1 and adds to 1, that's not going to work because multiplies to 1 is a 1 and a 1, and there's no way that will ever add to 1. So that piece is prime. So this is now factored. So now which formula is this? So when I look at this list, this is linear. This is quadratic. So I see the third one, non-repeated quadratic factor. This is not repeated. There's no power other than 1 over here. Non-repeated quadratic factor. So I'm going to rewrite this as, so it says, this is formula 3 I'm looking at. It says a over the one that's linear, so a over x minus 1 plus, and then look at what it says, bx plus c over the one that is quadratic. So x squared plus x plus 1. This is what I need to solve. So again, I'm going to multiply both sides by the LCD, and the LCD is always going to be this guy right here, just as a common. So I'm going to take both sides times x minus 1, x squared plus x plus 1. And there's two terms here, so x minus 1, x squared plus x plus 1, x squared x minus 1, x squared plus x plus 1. So when I do that, the left side, this all cancels, and I get 2x plus 4 equals. Over here, the x minus 1 cancels, so what's left is I have to multiply the a with all of that. So I get ax squared plus ax plus a. The second term, this piece cancels. So I have to take bx plus c and multiply it with x minus 1, which means I need to FOIL that out, right? So bx times x is bx squared. Bx times -1 is negative bx. C times x is positive cx, and c times -1 is negative c. Oh boy, what a mess. So basically what I have here, what I'm noticing is I have x squareds over here, I have x's, and then I have constants. So I'm thinking 3 equations, because look, I've got an A, a B, and a C. So I need to turn this into 3 equations. 1, 2, 3. So let's start with the x squareds. So I'm going to start up here on this side. The x squared, so here's an x squared. Here's an x squared. Is there an x squared over here for me to compare it to? Well, an understood 0x squared, right? So when I strip off coefficients, they're going to be equal to 0, because when I add these two up, I need to get 0 of the x squareds. So in other words, A plus B has to equal 0. There's 0 x squareds over there. So now I'm going to go pick on the x's. So here's an x, here's an x, and here's an x. And if you want to, you can rearrange the terms so they're all next to each other. I'm kind of leaving them in the order they are and just picking them off. And here's the x over here, look. So that means if I could add these 3 x's, I would get 2 of those x's, which means that positive A minus a B plus a C has to equal 2. A minus B plus C has to give me 2 of those x's, so 2. So in other words, we're stripping off the x's and just working with the a's, the b's, and the c's, and the constants. The last but not least is the constant, the terms that don't have any x's in them at all. So I see just an a there and just a negative c there. And those two terms, if I could add them or subtract them, I would have to get this constant over here, which is 4. So in other words, a minus c has to give me 4. So here's my system. 3 unknowns, an a, a b, and a c. 2 equations. It looks a little funny because you'll notice the first one doesn't have a c in it, the second one has all 3 variables in it, and the third one doesn't have a b in it. What that's telling me actually is that part of my problem is done. In other words, this one doesn't have a c in it, so I could choose to eliminate the c's from 2 and 3, and then I would have my a and b equation different. You remember how I numbered them 1, 2, 3, and then a and b. Unfortunately, there's a's and b's here as well. In other words, one of the steps that's been done for me in terms of 3 equations and 3 unknowns. Or, this one doesn't have a b in it, so I could choose this one as already reduced to two unknowns, and then take this one and eliminate the b. Well, I'm noticing that either way it's not too bad, because here this one doesn't have a c, so I could take these 2 and get rid of the c's and they're ready to go. Or this one doesn't have a b, so I can take these 2 and eliminate the b and they're ready to go. So it's kind of up to you how you want to do it. I'm just going to go, since this one came first and I saw it first, I'm going to go ahead and use it. So basically, equation 1 is like my a. The fact is that it already has only 2 variables in it. So I'm choosing to eliminate the c's. So this one's ready to go for my next set of eliminations. But I now need to take these 2, so 2 and 3, and eliminate the c's. So I think they're ready to go. I don't think I have to do anything. A minus b plus c equals 2. And this one says a minus c equals 4. It's ready to go. And when I do the adding of these, I get 2a minus a b, c's are gone, equals 6. So this is the first equation with only 2 unknowns, and the second equation with the same 2 unknowns. Again, I didn't have to manipulate this. It was ready to go, so I didn't have anything to do in that first step. So here's the 2 equations, 2 unknowns. A plus b equals 0 and 2a minus b equals 6. So tell me, do I want to eliminate the a's or the b's? The b's are ready to go, so I don't have to do anything to get the elimination to work. A plus b equals 0. 2a minus b equals 6. These are ready to go. I get 3a. B's are gone, equals, that's a 0, equals 6. Divide by 3, a is equal to 2. There's one of my first values, a is 2. What do I do with that? Again, just go to either this equation A or this equation B and plug it in. This one looks easier to plug in, so I'll plug this into equation A. So A is 2 plus B equals 0, so that means B is equal to negative 2. So I got A is 2, B is negative 2. So now I just need to get C. So I'm going to take B equals negative 2 and A equals 2. And I really only have one choice because I'm trying to figure out C. And well, actually, I could put it here or here. I do have two choices. That's nice. So what looks easiest to put it into? Actually, it looks easier to use equation 3. I could put it here as well, but I'll go ahead and use equation 3. And equation 3 only has A, which is 2, minus C, which I don't know yet, is equal to 4. I didn't even need B. So negative C equals 2, so that means C is negative 2. I will now check this here because I never actually used equation 2. So let's make sure. When A is 2, B is negative 2, and C is negative 2. Oh, these 2's. So that says 2 minus negative 2, so 2 plus 2, which is 4, and then 4 minus 2 is 2. So that looks real good. So there's my 3 solutions, but I'm not done yet, because remember, I'm going to cheat here so I don't have to write this all down again. Remember, it was this guy that I was trying to rewrite into these 2 forms, and all I have to do is replace A with its value and B and C with their value. So we said A is 2, so this is going to be 2 over x minus 1. And then bx plus c, where b is negative 2, so negative 2x, and then c is negative 2, so minus 2. So we just plug the values back in and you're done. That's it. And it's fine to leave the plus here and let the signs play out here. You could factor the negative out and turn that into a minus, but there's nothing wrong with leaving exactly like this. And in fact, in calculus, that's what you'll do, and you'll deal with that in the integral. So partial fraction decomposition. That one was a little more complicated, but we managed to get through it. We had 3 equations and 3 unknowns, and we had to deal with that, get a little more practice. And we managed to get this thing split apart. So let's go do number 3, see what it looks like. So that's the algebraic fraction or a rational expression that I want to try and do this partial fraction decomposition on. And again, I see an x cubed in that denominator, so that's an issue because I don't have a formula that goes with that. So it's kind of hinting to me that I need to try and factor this. And in fact, at the very least, this has a GCF. So let me write this down here and think about trying to factor this guy. So I can take an x out, right? And when I do that, I have x squared minus 2x plus 1. Can I keep factoring this? Because I need to go check on that, because depending upon what this turns into will depend upon which formula I actually use. And in fact, this is the easy big X. If I'm going to try it, multiply to 1, add to negative 2 is both negative 1s. We'll do that. So this is actually x minus 1, and then another x minus 1, which means that I really have here is an x, and then an x minus 1. It's there twice. So remember, the formulas split that into a different formula. So this is the formula where it says repeated linear factors Repeated linear factors in the denominator. So this is the second formula where it's a over the first one and then b over the second one and then a c over these guys squared. So this is what it looks like. So I'm going to go use that second formula to get this thing split apart. So let me get rid of this. So this is equal to, I take an a and I put it over just the x, and then I take the, so second formula is what I'm looking at, then I take the b and I put it over just the x minus 1, and then I take the c and I put it over the x minus 1 squared, over the linear factor that is repeated. And this is what I'm now going to try and solve. So again, I'm going to clear fractions, and the LCD is this guy right here. So I'm going to take every term, both sides, times x minus 1 squared, x minus 1 squared, oh, I keep doing that, x minus 1 squared, x minus 1 squared. So this should cancel entirely and just leave me with the x plus 2, which it does. This side I need to be real careful. Just this x cancels, so that means I need to multiply a with an x minus 1 squared. So I have to take a times x minus 1 squared. So do this, turn this back into what it came from. This was x squared minus 2x plus 1, right? So I have to take a times that. So when I do that, I get ax squared minus 2ax plus a. So be real careful with that. Again, the algebra getting in the way of the calculus, which is ultimately why we're doing this in the first place. So there's that one. And then the second one, one of these x minus 1 cancels, not both of them. So I have to take a positive bx times an x minus 1. A positive bx times an x minus 1. That's what that's given me. That's what's left here. So I just distribute the bx. So this gives me bx squared minus bx. So there's that one. And then the last one is the easiest one. This entire x minus 1 squared goes away, so it's just plus c times x. So plus cx. All right, so what have I got here? I've got a's, b's, and c's, so probably a system of 3 equations, 3 unknowns. I've got x squareds, and then x's, and then a constant. So I'm going to compare over here, but let me go grab the highest power here, which is ax squared. There's a bx squared. So there's my x squareds. When I add these two together, whatever a plus b is, it's going to have to equal what? How many x squareds do I have over here? 0. So that means this a plus this b better equal 0 because I need the x squareds to go away. So there's my first equation, a plus b equals 0. Now I'm going to go do the x's. So x's, I've got negative 2a of those x's, a negative b of those x's, and a c of those x's. And when I add a negative 2a and a negative b and a positive c together, I better get how many x's? 1. So this negative 2a minus b plus c had better equal 1. In other words, I'm grouping all the x's together. Negative 2a minus b plus c had better give me the coefficient of this x, which is 1. And then the last one is the constant. Well, there's only one constant over here, where a term with no x's in it. And the constant needs to be what? 2? Oh, that's nice. So a has to equal 2. Well, this is a system of 3 equations and 3 unknowns, but oh my gosh, we're like done almost. This one ended up giving me the answer for a. A is 2. And now I can plug that into here and I'll have b, and then I'll plug those into here and I'll have c. So I don't even have to do a system of equations and elimination. I'm ready to go. The fact is a is equal to 2. I will go plug this into equation 1. If a is 2, I have 2 plus b equals 0, so b is negative 2. And then I will plug both of these into equation 2 to get my c value. So negative 2 times a, which is 2, minus b, which is negative 2, plus c has to equal 1. Well, this gives me negative 4 plus 2 plus c equals 1. That gives me negative 2 plus c equals 1. So c is equal to, I add 2, I get 3. So I've got a is 2, b is negative 2, and c is 3. So that means, so I won't be lazy this time. That means, because this is too much to erase, that means x plus 2 over x minus, well, we'll write it the way it was, over x cubed minus 2x squared plus x is equal to a, which is 2 over x, plus b, which is negative 2 over x minus 1, plus c, which is 3 over x minus 1 squared. And there's my answer. I've taken it and I've broken it up into partial fractions. Each one of these are integrable in calculus, and so I've taken something that was very complicated and I couldn't integrate it, turned it into 3 pieces that I can integrate. So this partial fraction decomposition, I know by the time you get to Calc 2, when you use it, you'll have forgotten it. So hang on to the handout and see if that helps you to remember how to do things. And the last one here, number 4, let's go take a peek at it. It must be the one formula we haven't used yet because I tried to do one of each type. Oh gosh, the red is hard to erase. Okay, last one. So this is the guy they want me to do partial fraction decomposition on. So I'm going to take a look at this denominator. I have it factored at least partially. The question is can I factor it more? This is x squared plus 16. That's the sum of squares, which with my normal factoring techniques is not factorable. We're not going to turn it into imaginary factors. So this is as factored as it gets. And what this is a repeated quadratic factor. So that's that one we haven't done yet. That's the 4th one, repeated quadratic factor in the denominator, and it gets written as ax plus b over x squared plus 16, so over this guy not repeated, and then you do the cx plus d over the entire thing, which is x squared plus 16 squared. That's what I need to solve now. So how do I do that? I'm going to clear fractions, which means I'm going to multiply everything times that x squared plus 16 all squared. So every term, both sides, times x squared plus 16 squared. Okay. So what happens, this cancels, and I'm left with x cubed plus 1 over on this side. One of these cancels, so now I have to take ax plus b times x squared plus 16, so I have to FOIL that out. So let's see, ax times x squared is ax cubed. Ax times 16 is 16ax. B times x squared is bx plus bx squared, and then b times 16 is plus 16b. And then the last one, this all cancels, that's nice. And I get plus cx plus d. So there it is. Oh boy. So I've got A's, B's, C's, and D's. Uh-oh, 4 equations and 4 unknowns. We didn't review how to do that. Let's hope that some of this eliminates itself. So let's see, my first equation, the highest power here is cubes. So I've got an ax cubed. That's it. And look, there is an x cubed over here. So that means a has to equal 1. Well, that's nice. We got one of our answers already. Second one, x squareds now. So here's an x squared. I'm trying to figure out what symbol I want to use here. There's just one x squared there. Are there any x squareds over here? No, so that means bx squared has to equal 0x squared, which means b has to equal what? 0. Oh, that's nice. B is 0. Now we got 2 answers already. So system equation is going to be pretty easy, I think. 3 is x's. So let's see, I've got x there and an x here. I've got 16a of the x's and I've got c of the x's. Now, are there any x's over here? No, there's 0. So when I add these x's together, I should get 0, which means 16a plus c has to equal 0. 16a plus c has to equal 0. And so that one wasn't as nice. And then the last one is the constant. So here's a constant, no x, and here's a constant, no x. And there is a constant here, no x, it's a 1. So that means 16b plus d has to equal 1. So 16b plus d has to equal 1, and 16a plus c has to equal 0. But here we know what a and b are. So I don't really have a system that I have to solve, because this one, I can plug in the a and figure out the c, and this one, I can plug in the b and figure out the d. So I'm almost done. So first thing is, I know a is equal to 1. Second thing is, I know b is equal to 0. So now, in equation 3, I'll plug the a in. 16 times a plus c equals 0. So that says that 16 plus c equals 0. So c is equal to negative 16. So there's my next value. And now I have a, b, and c. I just need d. Well, here's the equation with d in it. And what do I need to plug into this to figure out d? I need to plug the b in. So I'll plug b into 4. And b is 0. So 16 times 0 plus d equals 1. Well, that's 0 plus d equals 1. So d is equal to 1. So I've got a is 1, a is 1, b is 0, c is negative 16, and d is 1. So that means that x cubed plus 1 over x squared plus 16 squared breaks up into a times x, so 1 times x, plus b, b is 0. So it's x over x squared plus 16 plus c is negative 16x plus d, which is 1, over x squared plus 16 squared. And there it is. That's my partial fraction decomposition. These are now 2 fractions that I can actually integrate, whereas before I was unable to. So that's section 8.5, partial fraction decomposition. It's a little more complicated, lots of algebra, and it's something that you need to know how to do when you get to calculus. So hang on to that in case if you need to review it. All right, so we've got one more section to take a peek at, and that is 8.6. And then I'll talk about the test. Is anything in chapter 8 going to be on this test? No. But after you take the test over the weekend or whatever on Friday, if you feel up to it, you need to start doing chapter 8 so that you don't get behind. So 8.6 is systems again. So this chapter 8 was all about systems. So systems with 3 equations, 3 unknowns, partial fraction decomposition, which depended a little bit at least on solving systems. Section 8.6 is solving systems of nonlinear equations. So they're not necessarily all going to be linear. So they aren't going to necessarily intersect in the nice thing of either in a point or an order triple or no solution or an infinite amount of solutions. It's going to be a little different because maybe we're going to look to see where a line intersects with a parabola, or where a line intersects with a circle, or where a parabola and a circle intersect. So nonlinear equations and where they intersect is what this section is all about. So it says that we need to examine the nature of the equations and decide if elimination or substitution is easier. So when they were linear, oftentimes elimination is easier. When they're nonlinear, oftentimes substitution is easier, because if one of them has an x squared and the other one doesn't, then how can I line up like terms underneath like terms and have everything I need to eliminate actually get eliminated? So I'm going to tell you right now that substitution is usually the easier way for nonlinear equations. And again, the goal is to generate one equation and one unknown that I can then solve. So I put down two steps here, or two comments here, because we're either going to do elimination or substitution, and like I said, most of the time it'll be substitution. But what I did comment on is, number one, sometimes thinking about the graphs, if it's not too tedious. So I don't want to do an exact graph that takes too long, but if I can at least think about what the graphs would be, so I can think about how many intersection points there might be, that might help me a little bit, because look at what number 2 says. Extraneous solutions, remember those things where they aren't really solutions? They can happen when you solve nonlinear equations, nonlinear systems, which means that you have to check all your solutions. You have to make sure that they work in both of the equations. So I have just 3 examples here that we're going to take a look at, and then we're going to quit. So this first one, so this is problem number 1, says y equals x squared plus 1 and y equals 4x plus 1. They want me to solve the system, which is what that little brace means, which means they want me to tell them where they intersect, if they do intersect. So before I even try and do this algebraically, I'm going to just take a quick peek about what kind of an equation is this and what would its graph sort of look like. I don't want to do it exact, but just an idea. And what is this? Well, this you're going to tell me is base parabola moved up 1. So it's just a right side up parabola. So just a quick little, this guy is, a right side up parabola. And this guy is what? This is linear, so it's a line. Is it vertical? Is it horizontal? Is it rising from left to right? Is it falling from left to right? It's not vertical or horizontal. It has a slope of 4. So that means it's rising from left to right, right? So here's possibilities that I can think of. They could not intersect at all, so I might get no solution. Or they could intersect at just one point where this touches the parabola just once. Let's see, I wore another shirt today. What does it say? Sometimes I like to go off on a tangent. I like to talk sometimes. And sometimes I do go off on a tangent. And so you can see there's my tangent line to that curvy little graph. Haha. We do have senses of humor. They're a little strange, but anyway. So it could be tangent where it just hits one. So I might only have one solution, one ordered pair, or this line might, instead of being tangent and just touching in one spot, it might cross through it twice. So again, I have it rise from left to right. This is right side up parabola. Could it touch any more? Can I get any more than 2 ordered pairs here? There's no way. At most, I'm going to have 2 ordered pairs. I can either have 2 ordered pairs, 1 ordered pair, or no solution. If I get 3 ordered pairs, then I know either I've done something wrong, or I better check because I've introduced an extraneous solution and I need to get rid of it. So at most, I'm going to have 2 answers here. And again, I will still check them to make sure that they work. So how do I solve this system? So again, I'm going to number this 1 and this 2. They look lined up, but they're not. And in fact, for elimination, this is an issue. How am I going to eliminate things? I can eliminate, it's just going to be more complicated to think about elimination. So I'm going to think about substitution instead. And substitution basically says, solve one of these for one of the variables and then plug that into the other one. Well, this is set up and ready to go. Each one of these is solved for y. So I'm just going to take equation 1 and put it into equation 2, I guess. It doesn't really matter either way. In other words, this says y equals x squared plus 1. So down here in equation 2, it says y, and instead of y, I'm going to write x squared plus 1 equals 4x plus 1. Or in other words, I'm taking those two and equating them because they're both y. And if they're both equal to y, then they're equal to each other. So this is what I have. What kind of an equation is this? It's one equation, one unknown, and it's quadratic. So I'm going to bring everything over here to the left. So x squared minus 4x. And what happens to the 1's? They go away, right? All right, well, I can do this. This is quadratic. I'm going to factor out the x. I get x minus 4. Using that zero factor property, this does play a part in the answer. So either x is 0 or x is 4. So this is looking like it's giving me two ordered pairs. I have to go figure out the corresponding y's. But I'm going to check them and make sure they work in both of the equations. Because again, even with this, I could have introduced an extraneous solution. So I need to be careful. So here comes my first ordered pair here. When x is 0, put it into either one of these, whichever one looks easier, and figure out the y value. Well, either one looks pretty easy. But I'll go ahead and pick equation 2 just because it's not quadratic. So this is y equals 4 times 0 plus 1. So that says y is equal to 1, right? So when x is 0, y is 1, which means the ordered pair 0, 1. Check it. Okay, you put that into here. When x is 0, y is 1. You need to check it. Must check in equation 1 to make sure that it works. So when y is 1, is x going to be 0? Yes, it works. So this is a good solution right here. So there's one place where they intersect. So maybe the line just intersects the parabola as the tangent to it, just in one point. But we have another answer here. We said x could also equal 4, right? So I'm going to go plug that in. So when I plug 4 into, again, it doesn't matter where you plug it into. If you plug it into equation 2, y is equal to 4 times 4 plus 1. So that gives me y equals 17. So that's the ordered pair. When x is 4, the y is 17. So does it work? Again, you need to check in the other equation, which in this case would be equation 1 again. So I put it into equation 1. Y is 17. Does that equal 4 squared plus 1? It sure does. So guess what? This line crosses, or the line and the parabola intersect, or the system of equation has two solutions. The ordered pair 4, 17, and the ordered pair 0, 1. So let's go look at number 2 and see what we can do with it. So this is y equals the square root of x, and x equals 6 minus y. So before I try to solve this algebraically, again, I'm going to just take a peek at the graph. It's good review. What is that? Y equals the square root of x. So this is one of the base functions we learned. Do you remember what it looks like? That was this guy. The sideways top half, the top half of a sideways parabola. That was y equals the square root of x. What's this guy? This is linear, right? And is it a special case, like vertical or horizontal? No. What's the slope here? What's the slope? So you have to do a little rearranging. If I solve this, if I put this y over here, then this x would be over here. So I think the slope is negative. So that means this line could either be here, and it doesn't intersect at all, or it could be here and it intersects in one place. There's no way for that to intersect more than once. So either once or 0. So I either get one answer or no answers. So that just as an idea as to what's going on here. So I'm going to go do this algebraically now. So this is just trying to do elimination on this. I wouldn't even know what to do. This is set up for substitution. So I'm going to use substitution. The fact is you have two choices here. This is solve for y, so I could plug this into here. Wherever I see a y, I'm going to put a square root of x. Or this is solve for x, so wherever I see an x, I could substitute 6 minus y. It's your choice. So this is problem 2. I'm going to call this equation 1 and equation 2. I'm just going to go ahead and plug 1 into 2. So I'm going to put 1 into equation 2. So equation 2 says x is equal to 6 minus y, where y is the square root of x. So that's what it now looks like. X is equal to 6 minus the square root of x. How do I solve that? What kind of an equation is that? There's only one unknown now, but what do you see in there? You see a square root, right? Which means that you need to isolate the radical. So this is a radical equation. Isolate the radical and then raise both sides to the appropriate power. So I can isolate this by moving this 6 over here. So let's see, if I do that, this becomes x minus 6 equals negative, and then the square root of x. And now I'm going to square both sides, the entire side. This entire side gets squared, and this entire side gets squared. So what happens here? What happens when you square this entire side? What do you have to do over here? FOIL it out. What is x minus 6 times x minus 6? I get x squared. I get a middle term, right? Negative 6x and then another negative 6x, so minus 12x. And then negative 6 times negative 6 is positive 36. So in other words, I'm taking x minus 6 times x minus 6, x squared minus 12x plus 36. Over here, what happens when you square a negative square roots of x? This is all one term. So I'm going to square the negative and I'm going to square the square root. So what happens when you square a negative? What's a negative times a negative? Turns into a positive, right? What happens when I square the square root? I just get the radicand, which is x. So what kind of an equation is this? It looks like it's quadratic. So I'm going to bring this x over here and see if I can factor it. So I subtract x, so I get negative 13x plus 36 equals 0. This is the easy big x, if I can get it done. Multiply to 36, add to a negative 13. That means they both need to be negative. Negative 4, negative 9 multiplies to positive 36, adds to negative 13. So this is x minus 4, x minus 9 equals 0. So that gives me x equals 4 or x equals 9. So I got two values for x. But what did we say about this when we thought about the graph? We said at most only one ordered pair, or maybe none. So I'm going to need to be very careful here because at least one of these is going to get eliminated, if not both of them, because at least one of them is an extraneous solution. So when x is 4, so here we go. Let's do x is equal to 4, and then we'll do x equals 9. I'll try to be a little more organized here on this one. So when x is 4, how can I figure out the y value? Actually putting it into number 1 isn't going to be too difficult, so I'll go ahead and do that. Y is equal to the square root of x, where x is 4. So what's y equal to here? 2. So the ordered pair is 4, 2, if it works. So that works in the first one. When x is 4, y is 2. You need to check in the second one to make sure before I circle that. So in equation 2, it says x, which is 4, is that equal to 6 minus y, which is 2. That works. 4 does equal. So it looks like it does intersect at 4, 2. So I better find that this one doesn't work. But let's go check it and see, because maybe I made a mistake. So let's see. When x is 9, we can put that into equation 1 as well. Y is equal to the square root of 9. So y is equal to 3. So that means my ordered pair would be 9, 3. So does it work? So you must check it in the other equation, which would be equation 2. X is 9. Does that equal 6 minus y, which is 3? Does that work? No way. So that one does not work. The only ordered pair where they intersect is 4, 2. So again, you have to check these. You often will introduce extraneous solutions. So we got one more of these, and then we're going to stop and talk about the test. So here's my system. Two equations, two unknowns, but they're not both linear, so trying to line this up would be a mess. But before I even try and do this algebraically, I'm going to think a little bit about the graphs. So tell me about this one. That's a line, right? That's linear. And its graph, its slope, I divide by 2. The slope is going to be positive. It's going to be a half, but it's just going to be small slope, so it's going to be not quite horizontal, but a little bit rising and to the right. So that's the first one. I probably have that rising way too much, but anyway, so there's the first one. The second one, what is this? This is a parabola, right? Right side up, upside down, to the left, to the right. Right side up, y and an x squared, so it's a right side up parabola. So again, a right side up parabola and a line that's rising from left to right, either they don't intersect at all, or it's tangent at some point where it hits just one point on the parabola, or the parabola at most could hit this guy in 2 spots. So 2 ordered pairs, 1 ordered pair, no ordered pairs, those are my possibilities. If I get 3 answers for x, then I know at least one of them has to go away, and it reminds me to check things as well. So those are my possibilities in terms of the graph. I don't want to do it that way. Graphing can be very inaccurate, particularly when your answers aren't nice. So I'm going to solve this as a system, and I'm not going to use elimination. I'm going to use substitution, because it makes life easier to do it that way. And the fact is this guy's already solved from y. So I'm going to take 2 and put it into 1 this time. So I'm going to take equation 2 and put it into equation 1. Wherever I see a y, I'm going to substitute this into it. So this immediately says 2 times y, where y is this whole mess, x squared minus 6x plus 9, and that has to equal x minus 2. So I substituted the expression for y into equation 1. So this looks quadratic to me, so let's see, I'm going to multiply, get 2x squared minus 12x plus 18 equals x minus 2. I'm going to bring the x and the negative 2 over here. So this is 2x squared. I'll subtract x, so that'll be negative 13x. I'll add 2, so that'll be plus 20 equals 0. And this is the harder big X, but I'm going to go try it. Multiply to 40, add to a negative 13. So a multiply to a positive, add to a negative, they both need to be negative. And I think negative 5 and a negative 8, negative 5 times negative 8 is positive 40. They add to negative 13, so that works. So let's see, you can either rewrite this into 4 terms and do grouping, or if I do that simplify idea, I put a 2x over here and a 2x over here. This won't simplify, but this will, into an x and a negative 4. So I think my factors are 2x minus 5, x minus 4 equals 0, which means that x is either equal to positive 5/2 or x is equal to 4. So 2 ordered pairs is what I'm getting here. But I'm going to have to check them, figure out the corresponding y value, and then check each one, because remember we said it might only be 1 ordered pair or none, but at most 2, so maybe these will both work. So again, I'm going to be organized here. So the first one is x is equal to 5/2, so I got to go figure out the y. The second one is x equals 4, and I'll go figure out the y, and then I'll check them and make sure they work in both of them. Which one is this easier to put into? Well, neither, but anyway, I'm going to go put this in number 1, because I know it's a fraction. And so if I put this into equation 1, which is linear, which maybe is easier, 2y equals x, which is 5/2, minus 2. So this says 2y is equal to, so 5/2 minus 2 is 4/2. So 5/2 minus 4/2 is 1/2. And then I have to solve this for y, which means I have to divide by 2, right? And if I divide by 2, that's the same as multiplying by 1/2. So in other words, if I take this times 1/2 and this times 1/2, this will give me y, and this will give me 1/4. So that means my ordered pair is 5/2, 1/4. And now I have to check it. So that's what I got putting it into number 1. So now I need to check in number 2 and make sure that it works, because maybe it's extraneous. So let's see, y is equal to, so 1/4 is equal to, oh boy, x squared. So 5/2 squared, I'm doing the hard one first. 5/2 squared minus 6 times 5/2 plus 9. So is 1/4 equal to, let's see, 5/2 squared would be 25 over 4. Minus 6 times 5/2 would be minus 30 over 2, which would be minus 15, right? I don't know why I did that. This cancels. So I get minus 15 plus 9. So is 1/4 equal to 25/4. So negative 15 plus 9 is negative 6, so minus 6. So is 1/4 equal to 25/4. How many fourths is 6? Oops. 24, right? 25 minus 24 is 1/4. Oh, it worked. Oh, that's a nasty one. And now I'm going to do x equals 4. This should be easier. I'll go ahead and plug this into 1. 2y equals x is 4, so 4 minus 2. So 2y equals 2, so that means y is equal to 1. All right, so that one's much easier. When x is 4, y is 1. So does that one work? So I'll go check this in equation 2. So y, which is 1, does that equal x squared? So 4 squared minus 6 times x, so minus 6 times 4 plus 9. So let's see, does 1 equal 16 minus 24 plus 9? Does 1 equal, so 16 plus 9 is what, 25, and 25 minus 24. Yeah, that one works as well. So it intersects in 2 spots, and those are my 2 solutions. So a little more work there. I always have to check those when I'm solving systems of nonlinear equations. So we actually finished everything we're going to do in chapter 8. So whatever that was, 8.1, 8.4, and 8.1, 8.5, and 8.6. Systems, mostly systems of different kinds of equations. I'm gonna now take the rest of the time to talk about the test. So let me go get out that information. And we'll see what little hints I can give you. I brought my whole notebook out here. I just have nothing to put it on. So let's see. What is this? Chapter 6 and chapter 7. Okay. Here we go. All right. So chapter 6 and chapter 7 is what this test is on Thursday. Hopefully you've already started to prepare for it. Again, you're going to come to the Zoom test meeting. I'm going to send the test to you early so that you can get it printed out and then join the Zoom meeting no later than the start time of your class. So if you're in my earlier class, your start time is 1:45. And if you're in my later class, your start time is 4:30. So again, you need to be there on time. If you're not in the Zoom meeting, either by that time or before that time, I'm going to start to deduct points, because the fact is you have the test in your possession and I'm not able to see what you're doing. So honestly, the sooner you can get that test printed out and on your desktop with your pencil and your calculator. So what I would do before I even get the test, I would have my desktop ready, completely cleared, just have my pencils there, my erasers, my TI-30X IIS calculator. That's it. Everything else cleared off. I mean, maybe, a ruler or something if you want a ruler for something. But the desktop should be cleared off. No notes, no books, no nothing. And I would have that all ready. So the minute I get that test, I would go get it printed, and I would put it on my desktop so that it's there and ready. I would come in on the Zoom meeting with my cell phone and get going. The sooner you can get the go-ahead from me that you're ready to take the test, the sooner you can start the test and be working on it. You get there at the last minute, then you're going to be held up, because I'm going to be dealing with one person at a time, trying to get them going. You have to show me your desktop, and then you have to get your phone set up. So I would play with my phone and make sure I know exactly how to prop it, or whatever it is, whatever system you're using to get it propped so it stays that way. so I can see your head, particularly your eyes, the front of your eyes, not a profile. I need to see your eyes because I need to see that they're looking down at your test. But you'll have to show me your desktop, and then you have to prop that phone so I can see your eyes and the tops of your hands. In other words, I want to see both hands at all times while you're taking the test. Sooner you can get that done, the sooner you can start the test. So I would not wait until the last minute. Let's see. The other thing that you will need to be aware of is when you're done, if you finish the test early, then you need to send me a private message on the chat that says, I'm done. Don't just leave the meeting. You leave the meeting and I don't realize it at the split second, then I don't know when you left. You could have left 15 minutes before I even realize you're gone. That's on you. So if you leave and you don't tell me you're leaving and get a response from me that says, okay, here's your deadline, then you've left inappropriately, and I'm probably going to give you a 0 because I don't know what you've been doing. So make sure that when you are leaving and you're done, that you tell me and you get a response from me. Let's see. What else do I want to say? Most of this has been outlined in the email you got Sunday night, but just as a reminder, there aren't going to be excuses on this one. So no excuses of, oh, well, I thought you knew I left, or my video keeps going in and out. So that's an issue. If you can't figure out how to get it so that your video doesn't go in and out, then I'm going to assume that your video is going in and out because you're doing inappropriate things with your phone. In other words, you cannot use apps on your phone and do things on your phone while it's showing me your face and hands. I will know. Your video will cut out. That happens more than once, and I'm going to give you a 0 on the test. So make sure that your video does not go in and out. And the excuse of, oh, my phone isn't working or whatever, that's just not going to fly. So you're going to have to figure it out way ahead of time. And if for some reason you can't get it figured out and you end up with a 0, that might be the time to think about that excused withdrawal, because unfortunately, this is how we have to do tests now. And in fact, the entire department has gone to this because we've all had issues. So let's see. In terms of what's covering on this, certainly anything on the quiz. So 6.1 through 6.5 is what that quiz was on. If it was on the quiz, it could very well be on the test again. So in other words, can you figure out a composite function and tell me the domain, which was 6.1? Can you figure out f of g of x, get it simplified, g of f of x, get it simplified, and then tell me the domain of that composite function? 6.2, do you know what a inverse function is? Do you know what it means to be one-to-one? I will comment on the quiz. When I asked you, is it one-to-one and why, some of you just told me because it passed the horizontal line test. Well, technically speaking, to be one-and-one, first of all, it needs to be a function. So you have to tell me that it's a function to start with, which means it passes the vertical line test. And then to be one-to-one, that means it also needs to pass the horizontal line test. So technically, you should have both of those in there because it passes vertical and horizontal line test. Can you take a function and decide, is it one-to-one? And then based on that answer, can you answer the questions that I want? In other words, can you give me the graph of the original function and then its inverse, and can you tell me the domain and range of each, and can you give me the equation of that inverse? Keep in mind, if it's not one-to-one, then it will not have an inverse. So if you answer no to one-to-one, then you're not going to graph an inverse, and you're not going to answer questions about a domain and range of an inverse, and you're not going to give me an equation for the inverse. If it is one-to-one, then you are going to answer all those questions. And be sure to carry over restrictions if there are any. So that was 6.2, 6.3, exponential functions. Let's see, what do I have written here? So can you graph an exponential function? If you're given one, and graph its inverse as well, because exponential functions do have inverses. In terms of 6.3, something like number 1 or number 2 could be one that I would make sure on the front side that I would make sure I know how to graph a basic exponential function. And then on the flip side of 6.3, certainly knowing how to solve an exponential equation by creating same bases. Yes, I would make sure that I can do those. So, and there were 8 examples there. I would make sure I know how to do all of them. I would practice them. Creating same bases, make sure you're showing me the steps. Don't leave a bunch of steps out, because if you leave a lot of work out, I'm going to assume that you are possibly using a calculator, or which you shouldn't be doing in terms of the formal solving of these. You're kind of plugging and guessing and checking. So I need to see the steps of the solution of creating same bases and then dropping the base. Let's see, 6.4, logarithmic functions. First of all, do you understand the restrictions on a log? There are 2 sets of restrictions. One is the base has to be greater than 0, not equal to 1, and the other one is the argument of the log needs to be greater than 0. So make sure that you understand that. Make sure that you know how to rewrite a log form into an exponential form and vice versa, exponential into log form. Let's see. And that base, the restrictions on the base and the argument help you to find domain of a log as well, the log expression. And then on that flip side, solving the log equations in 6.4, there were 1 through 8, and I'm going to tell you all of them. None of them are my favorite. You need to know how to solve a log equation depending upon what it looks like, and know if you need to check anything. You know, if the unknown isn't in the base or the argument, then you don't need to check the answer. If the unknown, the variable, is in the base of the log, then you have to make sure that that answer is greater than 0 and not equal to 1. And if the unknown's in the argument of the log, then you have to make sure that that answer creates a situation where the argument is greater than 0. And keep in mind, when you have x squared equals 9, there are 2 answers there. X is equal to plus or minus 3. Don't just write down one of them. I want to see the plus or the minus, and then I want to see that maybe you're eliminating one of them, or maybe you're telling me neither one of them are eliminated. So the work is very important. I have to see the work so that it shows the steps of the logical flow of the problem. 6.5, you need to know the properties in order to use them, to know how to expand a log into a single log into a bunch of separate logs, or take a bunch of separate logs and contract it into a single log. So again, on 6.5, I really don't have a favorite. You need to practice all of the problems that were in that handout and make sure that you feel comfortable with them. So starting with 6.6, this part wasn't on the quiz. So 6.6 is talking about solving log equations and exponential equations, adding a new way to do it. For instance, when you can't make same bases, or when you don't have a single log and then a number on the other side. So for this, I'm going to tell you my favorites on 6.6 are examples 3 through 7. So you don't need to practice 1 and 2 so much, but I would make sure I know how to do problems that are similar to number 3 through number 7. And I think I already told you number 7 is a favorite of mine. So I would make sure, however, that I know how to do all of them in terms of having a single log on each side and dropping the logs, or a single log on one side equal to a number on the other side, how to rewrite it. Creating same bases if I can, if it's exponential. If it can't create same bases and it's exponential, then I'll introduce logs on either side. And again, I need to see the steps. I need to be able to follow the logic of your solution in order for you to get full credit. 6.7 was the financial models, had lots of formulas. The formulas that you need to memorize are just 2 of them. One of them is the compound interest formula, the A equals P times 1 plus R over N all to the power of NT. The other one is the A equals PE to the RT. You do not need to memorize the effective rate of interest formulas. Okay? You just need to know compound interest and continuous compounding formulas and how to properly use them. So that's examples 1 through 4 on that handout. You need to make sure you know how to do. 6.8, you need to memorize that formula. A of t equals a sub 0 e to the kt, which is the formula for that exponential law of growth or decay. In terms of knowing how to use it, there were 4 examples there. I would make sure I know how to do all 4. I think I did hint that number 4 is my favorite because it requires you to go from a pure word problem where I haven't given you any formula, know how to put it into the formula, understand what a half-life is, and figure out what your K is without rounding it, and then put it in to figure out your final answer. But I would practice all 4 of them just to make sure, you know, I know what I'm doing. And then 7.2 through 7.4, the conics. Absolutely, there were 6 examples. There were 2 sideways parabolas, 2 ellipses, and 2 hyperbolas. I would practice all 6 of those and make sure I have them stone cold, because those can take time and you don't want to run out of time on the test. So I would make sure that I know how to graph each one of those. So I would practice all 6 of those. So I think I've given you all the information you need for the test. And again, you should already have all the rules. If you have a question, you should be emailing me or contacting me, just so that we're all on the same page. Again, this test is going to be with strict guidelines. And if you don't meet the guidelines, you will either receive a 0 or you will get docked 5 points for every minute late. And boy, I also will not accept any excuse for I couldn't get it submitted in time. So I left, I told you I was done, I did everything the way I was supposed to, and then half an hour later, I'm sending you an email all in caps saying, don't dock me, I can't get it submitted, I don't know what's wrong. You're going to get docked. It does not, I'm not going to accept excuses, because again, I can't tell what you're doing anymore. You're not in my view. You could be doing all sorts of things to fill in answers, and I'm not going to accept it. You'll get docked 5 points per minute late. Doesn't matter what the excuse is. Unfortunately, even if it's legitimate, which they haven't been, but at least I don't think they've been, it's not going to matter. So no excuses. So anyway, I'm being all nasty, so now I feel sad. So I have to make you guys feel happy again and make me feel happy again. So please study and do it the right way. I know a lot of you are, so I don't mean to be coming down on you. Good luck and study. If you have questions, please email me. I'm more than happy to help you or to look at anything you want me to look at. And I'll see you on Thursday. See you later.